So it is a generalization of your this, upper half plane with hyperbolic metric, and it is given by Promo. Okay. So let us begin with a geodesic metric space. And so let us fix delta greater than equals to 0. So X is said to be delta hyperbolic metric space if all the triangles, all the geodesic triangles are delta slim. Okay, so this is my definition of delta hyperbolic metric space. Okay, is it clear? So this is equivalent to saying that, so if I assume that all the geodesic triangles are delta slim, so this is equivalent to saying that, so triangles in X are delta prime thin, for some delta prime depending only on this delta. Okay. Yeah. So the definition of this hyperbolic metric space, so we can also assume the triangles are also thin. All right. Okay. So the example, so this already we have seen. So a tree is a zero hyperbolic metric space. Okay, so this already we have seen. Okay. And the next thing is, so this we are going to do. So you take this upper half plane with this Riemannian metric, so which is same thing as, so this two things are isometric to each other, or you take the unit disk with this Riemannian metric. Okay, so this is log 3 hyperbolic metric space. Okay, all right. So so how we are going to prove this thing? So I'll work with this disk model of this hyperbolic plane. So let us first draw this disk. Yeah, so this is my this unit disk. Okay, and now so you draw a geodesic triangle. So let us draw a geodesic triangle. So it will look something like this. Okay, so this is my geodesic triangle. Okay, so I want to prove that. So this is this log 3 slim, right? So again recall. So what is the definition of slimness? So this, let us call this to be XYZ. So triangle XYZ is delta slim if any side of this xy, this triangle xyz is contained in delta neighborhood of, so here closed the delta neighborhood of union of other two sides. Okay. So this is the meaning of delta slimness. Okay. All right. So in fact, so what will prove that, so this triangle, it is, in fact, it is a delta thin, where this delta is log 3. Okay. So how we are going to do this thing? So first, so what you do, so you can embed this triangle in a bigger triangle. So this you can extend this geodesic. You can, yeah, so extend this geodesic. No, this one. Or yeah, so let me first extend so all this geodesics. Okay, all right. Okay, so now what I'll do, so I'll join this by these two things. So you have extended this thing. So let us call, so this point, so this points are at boundary. Okay, so it is at S1. So these are at boundary. So this black triangle, so it is inside. So this delta XYZ. So this delta XYZ. So this is inside this poichoid disk. So all the vertices, so XYZ, it belongs to your this poichoid disk. Okay. So now you can extend the sides like this, and so we'll get another triangle. So this delta XYZ is contained in this delta PQR, where now this PQR, it belongs to your this circle. Okay. So this all as you can do. So first we have started with this triangle delta XYZ. So then we have this embedded this triangle in a bigger triangle PQR, and then what we are going to do, so we'll prove that this delta PQR, so this is delta, this is log n3 slim. Okay, so what will prove that, so this PQR, so this PQR now it lies in the circle. So this is log 3 thin, we will prove. Okay, and this will imply that, so this will imply that, so this triangle PQR is log 3 slim, and which will imply that the smaller triangle is also log 3 slim. Okay. Yeah. So now what we have, so again, let me draw this thing. So this is my poichoid disk. And now we have these 3 points in the boundary PQR. So this triangle is also called ideal triangle. Ideal triangle means vertices of those triangles are at infinity in the circle. Okay. Yeah. So I want to prove that this triangle is your log 3 slim. Okay. So now we are going to use the this property of this Mobius transformation. Okay. Yeah. So
So you extended the sides in both sides. You have extended side of a triangle.
so I got this 3 points PQR. Okay. And yeah, right. So this, Okay, sorry. So one mistake I have made. Thank you. So you will not get this thing. So this will be, in fact, it is a infinite. So this side will be something like this. Thank you. Okay, so this is something like this. Is it okay right now? I've not extended this part. This is not needed. So the idea is to embed this delta XYZ inside a bigger triangle whose vertices lie in the circle. So this angle, this will be, so this picture is little bad. Maybe I can. Okay. So this you extend like this. So this will be 90 degrees. This point is my R. Okay. Yeah, just 1 minute. So I messed it up. I think the previous one, what I wrote is correct. Okay, so what I am doing here, sorry. So I am extending this YZ part. So this you are getting. So this is my R, right? Okay, so this is my R, and I am extending this XZ. Okay, so this is my P. So P you got. Okay, and now what you do, you join this P and R by infinite geodesy. Fine. Okay.
Yes.
Yeah. So you got this PQR. Now join this P and Q by again by infinite geodesics. So yeah. So previously what I said, it is correct.
So, sir, after joining P and R, how do I guarantee that this triangle will be inside that the bigger one? I mean, is it very easy? I can't see that.
So yeah. So this PRR joining P and R. Okay. So it will be not something like this. So R is here. So it will not be something like this, right? That can't be possible. So maybe you can check this thing. Yeah, so please check it. So it will, in fact, so this delta XYZ, it will be inside this PQ one.
So, or one thing we can do, we can take one vertices to the center, right? That I can do, right?
Take one vertex, yeah, that also you can do. So what you can do here, so you can move this triangle XYZ such that one vertex, it will be a center. Yeah, so that also you can do. So if you are, so without loss of generality, I can assume one of the vertex to be at origin, something like this. So this is 0, and this is, let us call Y bar, Z bar. Yeah. So this is X bar. Yeah, and now what I'm saying here, so you extend this thing. Okay. You extend this part also, one of this thing. And now what you do, so you join, maybe I'll do this some other. So join this thing. So you'll get an ideal triangle, right? Is it okay?
Yes, yes.
Yeah. So
Yes.
always I can, so just maybe.
I can take the bisector of that angle and extend, right? That you
Correct,
can.
that also you can do. Okay. All right. So this always you can do. So now the problem boils down to this ideal triangle. So this vertices of this triangle are at infinity.
Another thing, what do you mean by some thin triangle for infinite triangle? I mean, suppose you have an ideal triangle, what do you mean by it is delta thin?
Okay, okay. So I'm coming into that. Just give me some time. Okay. So now given this triangle, so you know that this this PSU11, so this is a subgroup of isometry of this Poincare disk, and uh, so an element of this thing is of this form, right? So A Z plus C bar Z plus A bar. So mod of A square minus mod of C square. So this is equal to your 1. Okay. So this is again a Mobius transformation, okay, from disk to disk. And it has this property there. So if you are given any 3 points, let us take P prime, Q prime, R prime, okay. So yeah, so it will again, so f of P prime, again it will be an, yeah. So f of P prime, f of Q prime, and f of R prime. So this again, it will lie in the circle, okay. So this is one thing. And so given this, so given this, let me write like this, where this P is not equal to Q, not equal to R, and again you are given this thing where this P prime not equal to Q prime, not equal to R prime. So then, so there exists an isometry. So there exists an element of this PSU11 which takes this P to P prime, f of Q to, sorry, f of Q to U Q prime, f of R to U R prime. Okay, so this need to be checked. Okay, so if you want, we can do it in tutorial, this part. So this is yeah, so property of this Mobius transformation preserving this disk. Okay, so suppose you know this thing. So suppose you know this fact. So now what I'll do, so I'll take this points P prime, Q prime, R prime to be your favorite points. Okay, so what I'll do, okay, so I'll take this first point 1, and I'll take this points with the such that, so this is my origin, such that this angle is your 120 degree. Okay, so 3 equispaced points in the circle. Okay, so this 3 points I'll take. Okay, and yeah. So let us give some name here. So this is my, let us call it to be my P prime. This is my Q prime, and this is my R prime. Okay, so we have an isometry which takes, so this triangle to your this triangle. Okay, so now the picture is very nice. Okay, so there exists an isometry which will take this triangle to your this triangle that I am saying. Okay, so now the problem boils down to prove the things for this nice triangle, this triangle. Okay, all right. Okay. Okay, so this part I have worked it out. So now you can, so now the argument is very easy. Okay, so let me draw another picture of this. Oops, yes. Okay, so now you have this ideal triangle. So you have this ideal triangle. Okay, and so now note that, so due to symmetry, so this length will be same as this length, although the picture is little bad. So this length, if I call it to be A, so this will be again equal to A. Okay. All right. So this distance, again, this will be your A. So this is my origin. Okay. So distance of origin to your P prime Q prime is same as origin to 1 to Q prime. Okay. Or so therefore, so if I call this point, let us call this to be my C1, and this is CQ prime, something like this. Okay. So therefore, so what I have now, so I'll just concentrate on this part. Okay, so I'll just concentrate on this part. So let me redraw this thing again in the pointer disk. Yeah, so this is something like this. So this distance is A, this distance is A, and yeah, so we have something like this. So this distance is A, this distance is A, right? So this is my C1 and this is my CQ prime, and this point is my P prime. Okay, so distance of C1 to CQ prime, so this is at most twice of A, right? So this distance is at most twice of A. So now what I'll do, so I'll just move T distance up. So this distance T and this distance T. Okay, so this distance, so let us call C1T and CQ prime T. So these 2 points, so this distance, you can check that. So this is again less than equals to, because these two geodesics are asymptotic to each other. Okay, so this is less than equals to twice of A. Okay, so this is the meaning of this triangle is thin. It means that, so again you can split. So Rakesh, you asked this question, right? So what do you mean by thinness
Yes.
here? So again you can split this ideal triangle like this. Okay, so you'll get these points. Okay, so now you do not have the concept of distance of P prime to C1, that is infinite, but I'm not saying that thing. So, but if you move T distance, so if you just move T distance up here and T distance up here, so this distance will be less than equals to twice of A, correct? Okay, so therefore,
In general, there is no notion of
yeah,
some
so in general, yeah,
for ideal.
so thinness you can't, yeah, so that definition you cannot give, but something similar you can. Okay, and same thing happens for this side also. So if I move, say, T prime distance this side and T prime distance this side, so this distance, so this will be at most twice of A. Okay, so therefore, so this, what I have proved that, so this triangle P prime Q prime 1 is 2A, let me call slim. So this all of you agree, right? So I'm not going to thinness part. So this all of you agree. So if I take any point, suppose in this geodesic, P prime to Q prime, so we'll get a point either in one P prime geodesic or one Q prime. So the distance is at most twice of it. Okay. So therefore, what I have proved that, so this triangle is, this ideal triangle is your 2A slim, and this triangle is isometric to this PQR triangle. So this PQR triangle. So therefore, it will be also your 2A slim. Okay. And this triangle XYZ. So this is embedded in PQR. So this will be also 2A slim. So only job is to prove that this A is equal to your half of log 3. Right. So at least now you can visualize that why the triangles are slim in this, uniformly slim in this poikiloid disk. Okay, so now this computation, so this part I have already done. So yeah.
Hello, sir.
Yes.
So that
This-
distance you have written just the previous page. Yes, yes, yes. So that distance you have taken a d2 of O comma P prime Q prime is equals to that is equals to A. You have taken A. So that is the Euclidean distance, no?
No, you can take, no, that is not Euclidean distance. This the, so if I take Euclidean distance, it is same, and hyperbolic distance will be also same, right? Both Euclidean distance are same. So okay, so I'm coming to that thing.
Okay.
Okay. So here, so that triangle, so that ideal triangle I have drawn here. Okay, so now what you want? So you want this distance. So you want this distance, right? Okay, so this I have called it to be A. Okay, okay. So if you compute, so all this computation you can check. So if you compute, so this point, this foot of the perpendicular, I have noted it as O prime. So Euclidean distance between O and O prime is 2 minus root 3. Let us call it to equal to R. And the hyperbolic distance between O and O prime, so this in fact it will be log of 1 plus R by 1 minus R. Okay, and yeah, R is this thing. So this this distance A is equal to your, so hyperbolic distance is your half log 3. Okay, so therefore we have proved that the triangles are log n 3 slim in poikiloid disk. Is it okay?
Yes, sir. So that's why I'm confused. The Euclidean distance and hyperbolic distance, there is a relation here. So this is the
Yes,
relation,
correct.
right?
Correct. This log of 1 plus R by 1 minus R. Okay. Okay, good. So what we have proved? So we have proved this example, the second thing. So we have proved that this poikiloid disk with the hyperbolic metric is log 3 hyperbolic metric space. Okay, all right. Okay, so maybe something I'll say it beforehand. Okay. So another example. Okay, so before giving this example, maybe I'll just write this thing. So maybe I'll write this statement. So hyperbolicity is quasi-isometry invariant. Okay, so by this, what I mean, so if I take a hyperbolic metric space, okay, so if I take a hyperbolic metric space x1, so this is delta hyperbolic, okay, and suppose there exists a quasi-isometry from x1 to x2, so this is another, x2 is another metric space. So we take both this x1 and x2 be your geodesic spaces. So phi is a quasi-isometry. from x1 to x2. So you will get some. So there exists delta prime depending on this delta, such that this x2. So this x2. So this will be delta prime hyperbolic metric space. Okay. So in the morning, so you have learnt about this quasi-isometric, right? So this hyperbolicity is quasi-isometric. Okay, so now you can have, suppose you know this fact, so now you can have many examples. Okay, so you have said that this, so if I take any tree, so this is a zero hyperbolic metric space. So in fact, so if I take R, so this is a tree, so this is zero hyperbolic metric space. And this, in fact, so this is a quasi-isometric too. So if I take any strip like this, okay, so it is R cross some interval. So these are quasi-isometric. So again, so this will be a hyperbolic metric space. Okay, so this part is easy. Okay, so now, okay. Okay, so let us assume this thing. So hyperbolicity is quasi-isometric invariant. So let me, okay, so another example. So let us take, so let SG be a closed orientable surface of genus G, where this G is greater than equals to 2. Okay, so again, this is a crucial fact. So this pi1 of SG acts freely by isometries on the Poincare disk. Okay, so this is my Poincare disk, and the action is properly discontinuous and co-compact. Okay, so by Milner's work lemma, so what Sri Krishna today morning proved. So by Milner's work lemma, so this so Cayley graph of this pi1 SG. So with respect to the standard generating set, so this I'm not denoting. So the Cayley graph of this is quasi-isometric to your this Poincare disk. Okay. So this proves that, so this proves that okay, so this proves that Cayley graph of this fundamental group of the surface is a hyperbolic metric space. Okay. Any question? Okay. Okay. So okay. So now if I assume this thing, I can have something more also. So hyperbolicity is quasi-isometric invariant. So I can define what you mean by hyperbolic group. So what is the definition of hyperbolic group? So let G be a finitely generated group with a finite generating set S. Okay, so G is said to be a hyperbolic group. So if the Cayley graph of G with respect to S So if the Kelly graph Kelly graph of G with respect to S is a hyperbolic metric space. Okay, so now the question is why this definition well defined, in the sense that, so if you change the generating set, okay, so so with respect to that generating set, is that space, will it be a hyperbolic metric space? Okay, so this fact also you have seen. So if S prime is another finite generating set of G, okay, so then, so the Kelly graph of G with respect to S is quasi isometric to the Kelly graph of G with respect to S prime, right? So therefore, if I assume one Kelly graph to be hyperbolic metric space, so the other Kelly graph, so this will be also a hyperbolic metric space. Okay. Also, okay. So also note that, so when I say that X is a hyperbolic metric space, means there exists a delta greater than equals to 0 such that X is a delta hyperbolic metric space. Is it okay? Okay. All right. So now what are the examples of this hyperbolic groups? Okay, so again, so this part already you have seen. So if I take any free group, so if I take any free group of finite rank, so why it is a hyperbolic group? So anyone, please.
The graph
So why
is tree.
it is the Kelly graph? It is a tree, right? So therefore, so with respect to the standard generating set, the Kelly graph is a tree. So therefore, it is a free groups are hyperbolic groups. So other examples are, so if I again take the fundamental group of this genus G surface, so it is closed orientable surface where this genus is greater than equals to 2. So this is a hyperbolic. Okay. So what about non-example? So can you give an example of a group which is not hyperbolic? Yes, anyone? So can you give example of a group which is not hyperbolic? So if I take any finite group, so this is obviously it is a hyperbolic. Right?
Infinitely generated groups will not be hyperbolic.
No, my world is now the group generated, the finitely generated groups only. So you have to give example from finitely generated groups. So in order to get an, which is not an example, not a hyperbolic group, so you have to think in terms of a space which is not hyperbolic metric space. Okay. So first of all, can you give me a space which is not a hyperbolic metric space?
So in R2, you can find big triangle.
Yeah, so R2 with Euclidean metric, it is not an hyperbolic metric space, right? So you will not get a single delta for which all the triangles will be delta slim, right?
Yes.
Z
The
direct
Kelly graph
some
of
Z.
Z direct sum Z
Yeah.
is isometric to
So
R2.
so Z direct sum Z. So this is quasi isometric to your R2. Okay, so R2 is not a hyperbolic metric space. So this will imply that Z direct sum Z is not a hyperbolic group. Okay. So in fact, so there is a very strong result. So maybe I'll write this fact. Don't know I'll have time to put this or not. So take any group. So let G be a finitely generated group such that so Z plus Z is a subgroup of this G. Okay. So then so this G is not a hyperbolic group.
So can I say this? If I have a group G which has a subgroup which is not hyperbolic, then the original group G itself a non-hyperbolic. Will it happen?
No. Yeah. Okay. Maybe I have that result. So this result is by Rips. Okay. So it says the following. So let Q be a finitely presented group. Okay. So then there exists a short exact sequence like this. Short exact sequence of finitely generated groups. 1 K G Q. So Q sits in the quotient such that this G is a hyperbolic group and K is a finitely generated group. I think yeah, K is a finitely generated group. So what he has shown, it is generated by 2 elements, but K is not finitely presented. Okay. So this proves that. So K is not a hyperbolic group. Why? So one can prove that a hyperbolic group is always finitely presented. Okay. So this is a very strong result by Rips. Okay. So a hyperbolic group, it can contain a non-hyperbolic subgroup. Have I answered your question? Is it okay? Okay. All right.
So, and how do we prove that fact? I mean, is it very hard?
This Rips thing. This fact or which one?
The previous one, that Z
Oh, previous
direct
one.
sum Z is a subgroup.
Okay.
I understand. If it is a finite index subgroup, then I understand. Yeah.
Okay. So yeah. So okay. So maybe I said something. Okay. So this part is easy, and something converse is also true. I think the converse part is a little bit hard. Maybe right. So if G is a hyperbolic group, if G is a hyperbolic group, then Z plus. Okay, so then G does not contain obtain Z direct sum Z. Oh, just wait a minute. Yes, yes. Okay, yeah. I think I'm right. Yes.
Sorry to interrupt. I got disconnected. Could you show me your previous slide?
Which one? Okay, this one. You asked this question, right? So, suppose a hyperbolic group, it does not so can it contain a subgroup which is not hyperbolic? Yeah, that fact is true. So this is a result by Rips. So let Q be a finitely presented group. So then there exists a short exact sequence of finitely generated groups, such that this Q is sitting as a quotient. G is a hyperbolic group. G is an extension group, and the kernel is only finitely generated group. It is not finitely presented. So therefore, it is not a hyperbolic. Yes. Okay. All right. So let us move further. So again, I will come back to this hyperbolic group thing. Yeah. So this one statement is about this result. So from this RIPS result, you can construct many hyperbolic group, right? So you start with your favorite finitely presented group. So from that, you can build a hyperbolic group. Okay. So you can construct many hyperbolic groups, and the proof for this requires small cancellation theory. Okay? So maybe Professor Subhabra Prakash will be dealing with this thing. Okay, all right. Okay. So now let me move to this divergence of geodesics in hyperbolic metric space. Okay. Here. Okay. So what do you mean by divergence of geodesics? All right. So let us first start with this R2 with Euclidean metric. Okay. So first, so let us first observe something before going to the definition of this divergence. So let us first observe something. So this is my origin, and let us take two this line segments starting from this origin. Okay, and they are making this angle theta naught. Okay, and now what you do, so you draw a ball around this of radius r around this origin. Okay, and let us take a path alpha. Okay, so let us take a path alpha outside this ball. Okay, so what we have done, so we have started with two geodesics starting from a point O, and so those two geodesics are of length. The length of those two geodesics are same, and they are making an angle theta naught. And alpha, it is a path lying outside this ball of radius r around origin. Okay, so yeah, so in this R2 with Euclidean metric, so obviously, so the length of alpha, so this will be greater than equals to your length of this circumference, this part of the circumference, right? This blue thing. Okay, and length of C, so this is equal to R theta naught. Okay, so again note that, so this distance is your R, right? So R is the radius of this ball. Okay, so here, so what we have here, so this thing, it is a linear function on the radius of this ball. Okay, so length of alpha, it is greater than equals to this r theta naught. So here,
Why is the first inequality L alpha is greater than or equal to LC?
this you can check. I mean, So if I take any ball here,
Oh, you are
and if I take
Euclidean
Euclidean
case.
case,
Okay,
yeah, right.
I
If
see.
I take, so this all, okay. So length of alpha, it is always greater than equals to length of c, and this is equal to your r theta naught. So this, it is a linear function on in R. So let me say this term before defining. So geodesics diverge linearly here, okay, because this function, it is a linear function on this R. Okay. So now let us try to do it in the this hyperbolic case. Okay. So let us draw the same picture here. Okay. So we have this Poincare disk. So don't first of all look into this red thing. So this computation I have done. Okay. So I have taken this Poincare disk, and so again, so I have chosen this two geodesics of length A. So these are my hyperbolic length. Okay. And so I have drawn a circle of radius A around origin. This one. Okay. And alpha, it is a path again lying outside this ball around origin of radius A. Okay. Okay. And again, I have denoted the circumference as C. Okay. So we have the same kind of picture here. Okay. So first job, what Rakesh asked, so is to check that this length of alpha is greater than equals to C. Okay, so this computation I have done. So length of alpha will be equal to this thing. Okay, so this one can check that this is greater than equals to this this part, and yeah. So from some computation it will come. So I'm not going to that thing. You can look into that later. So length of alpha is greater than equals to your length of C. Got it? Okay. So now what is the length of the C? So yeah. So suppose so I have drawn like this. So if this distance is your A, so this point in D, so this it will be your A, right? So this I have taken on the this real axis. Okay, so this point will be your A, and if I take this angle to be your theta naught, so this coordinate of this point will be A EI theta naught. Okay, and now I want to compute the length of the C. Okay, so so this length of C, yeah, so this will turn out to be uh, so mod Z is equal to A on C, right? So therefore we have this thing here. Yeah, so you have this thing here, and so maybe yeah. So I have taken the root of this thing. So maybe it is coming from here. Okay, so this, so dz, so this will be, yeah, so dz, it will be your A, yeah, so dz, so this will be your, so r is fixed here, so it will be A ei theta d theta. I mean, I will also come out, but you are taking mod, so therefore we have this thing here. So length of C, you can compute it to be this this one, so twice A theta naught divided by 1 minus A square. So this is my length of C, and okay. So this A, I have taken it to be, let us first take it to be Euclidean distance. So that's why this coordinate is your A. And let us take this R to be the hyperbolic distance between 0 and A. Okay. So this you can check that this R will be in fact log 1 plus A by 1 minus A. Okay. So yeah, you can expand all this thing. So A will be equal to tan hyperbolic R by 2. You can put, so put this thing here. So length of C is theta naught sine hyperbolic R. So now R, now it is the distance from, so R is the distance of origin to your A. Okay. So what we have here, so length of alpha is greater than equals to length of C, which is equal to your theta naught times sine hyperbolic R. Right. So again, sine, So I'm writing the definition of sine hyperbolic r here. So this is greater than equals to this thing. Okay. So let me draw it again. So I have this Poincare disk. So I have this is my origin, and I have taken two geodesic rays making an angle theta naught, and this Euclidean distance, or let us take Euclidean distance. I have taken it to be a, and the hyperbolic distance is r. Okay, and now I'll take this ball of radius r, and now what I'm doing, so I'm taking a path alpha outside this ball. Okay, so what I have shown that, so length of alpha, okay, so this is greater than equals to theta naught by 2 e to the power r minus 1. Okay, so this right hand side, so this is exponential. Okay, so this is the exponential function of this r. So therefore, so again, what we say, so geodesics in the Poincare disk diverge exponentially. Okay. So I'll come to the formal definition in a moment. So now let us move to your delta hyperbolic metric space and try to see the same thing there. This one. So I have given here the definition of divergence function. So I'll come to the definition later. So let me first do something in your delta hyperbolic metric space. Okay, fine. So I want to do the same kind of thing there. So let me draw a picture. Okay. So, okay. So now, so what you do, so start with a delta hyperbolic metric space. Okay, and now you take two geodesics. Starting from a point. From let us fix a point and call it to be base point. Okay, so now we do not have this concept of angle here. All right. So what I'll assume here, so let us assume, so there exists some point. So let us call this point. So I have called this geodesics to be your gamma and gamma prime. Okay, and let us call this to be my. So let us assume that we have 2 points such that this distance is greater than 2 delta plus 1. Okay, so this distance is greater than 2 delta plus 1. Oops. Okay. And now let us take this point. So this is gamma r plus r and gamma prime r plus r. Okay, so distance of P2 gamma r plus r is equal to distance of P2 gamma prime r plus r, and which is equal to your this thing. Okay, all right. So now what I'll do, so I'll take a ball of radius. So take this ball around P of radius capital R plus small r. Okay, and now take a path alpha which is lying outside. Okay, so which is lying outside this ball. Okay, so this intersection alpha is only equal to your these 2 points. Fine. Okay. Yeah. Okay. All right. So we are going to do same thing here, same kind of thing we are going to prove. So, so length of alpha, so what we are going to show, so this length of alpha, this is greater than some function, some exponential function of r. Okay, so with some constant, it can come some, so k times some exponential of r. So this kind of thing we are going to show. Okay, but so you have this diagram now. So first observation is, okay, uh, so length of alpha, so this is always greater than equals to 1. So why this is true? So length of alpha, so this is greater than equals to u 1. So alpha, it is a path lying outside this ball. Fine. And first claim is length of alpha is greater than equals to u 1. So why this is true? So if this is, so if length of alpha, if it is less than 1, so in fact it is greater than 1. So if it is, if length of alpha, it is less than equals to 1, so then, so this will imply that, so then distance of these 2 points, so this will be at most 1, right? So this will be at most 1. Okay, so now what you do, so you join these 2 points by a geodesic. Okay, so and the length of geodesic, so this is at most 1. So if we assume that length of alpha is greater than, less than equals to 1, right? And now if I take this triangle, so if I take this triangle, okay, so if I take this triangle, so do I get any contradiction? So this side, length of the side is at most 1. Okay, so now we have this triangle. So here you have 2 points which are greater than 2 delta plus 1. So you know that this triangle is a delta hyperbolic metric space. So this triangle, so this will be your delta slim, right? So this triangle, so this will be your delta slim. Fine. So for this points, so for this point, okay. So I'll get point here, or yeah, so this is 2 delta plus 1 greater than 1. So I'll get a point here. So this is at most delta. Okay, so I'll get a point here. So this is at most delta. So observe this thing. So because of the slimness, so I'll, for this point, I'll get a point here. So this is at most delta, and this will be at most delta. And because this side is at most 1, so this will prove that, so yeah, so this will prove that, so this will imply that, so distance between gamma r and gamma prime r, so this is at most 2 delta plus 1. Okay, so this is coming from the slimness of the triangle P gamma r plus r and gamma prime r plus r. Okay, slimness of this triangle. Okay, all right. Okay, so therefore, so we have a contradiction. So we have a contradiction here. So therefore, so what we have, length of alpha, it is always greater than equals to. So this part we have shown. So length of alpha, it is greater than equals to. So let me again draw this picture here. Oh, sorry. Okay. So we have this picture here. So join this 2 points by a geodesic. Okay. All right. So this distance, so this is greater than 2 delta plus 1. Okay. All right. So again, if I consider this triangle, so we'll get a point. So we start with this thing. So we'll get a point here. So so this distance is at most your delta. Okay. So this distance is your at most your delta. Okay. So now what I am going to do, so this is my path alpha. So I'll take a midpoint of this path alpha. So M is a point on alpha such that length of alpha restricted to this portion is same as length of alpha restricted to this portion. Okay. So now what we are going to do, so we join these 2 points by geodesics. Okay. So now we have again this triangle. Okay. So this triangle is again is your delta slim. Okay. So now for this point, so you'll get a point either here or here such that the distance is at most delta. Okay. So let us assume, so this distance is at most delta. Okay. Now you continue this process. So once you have this point here, so you again make a subdivision of this subsegment of this alpha in 2 equal lengths. So again, you have take the midpoint of this thing. So you have this thing and you continue this process. So you continue this process. So again, for this point, we'll have a point either here or here such that the distance is at most delta. Okay. Oh, so up to what stage will continue? Okay, so we have assumed that this length of alpha, so this is greater than 1, right? So we'll get, so there exists n, natural number n, such that, so this 2 to the power n minus 1 will be less than length of alpha, and it will be less than equals to 2 to the power n. Okay, so this implies that half is less than length of alpha by 2 to the power n less than equals to 1. Okay, so you continue up to the nth time. Okay, after n you stop. Okay, so after that what we'll have, so we'll have a some kind of this nth subdivision of this alpha. Okay, so now we are going back to the note. Okay, so this part is explained. Yeah, so we have subdivided this alpha in this way. So length of alpha is greater than 1. So we have subdivided this alpha in this way. And yeah, so we have this thing. Yeah. Okay, so we have this picture here. So this M0, so these are the midpoints of those subsegments of this alpha. Okay, all right. Yeah, so now after nth step, so what we'll have, so this points I have called it to be, so first point, so this point is your V0, so then your V1, and yeah, so then you have this Vi. So we have continued this process till n steps. So distance between Vi and Vi plus 1, it is at most delta. Okay, and after nth step, so note that, so distance of this Vn, because okay, so what we'll have, so after nth step, so this subsegment, so this will be length of this thing will be at most equals to 1. And now what we have here, so we have a point in this geodesic, so which is your this Bn. So naturally, so because the length of alpha, so length of this subsegment is at most 1, so distance of Bn to alpha, so this will be also at most your 1. Okay, so distance of Bn to alpha, so this will be your at most 1. Okay. Yeah, so this point I have, that picture I have called it to be P. So let us call it to be X here, or you can call it to be P. So distance of the base point to your alpha. So this is by triangle inequality. So first this distance, so then this distance, then this distance, you continue like this up to n step. So what will have? So this distance is your R, and this is at most your delta. So what we have is R plus n plus 1 delta plus 1. Okay, so you have this thing here, and also note that so this alpha, it lies outside the R radius ball around X, right? So alpha lies, yeah, so this I have called it to be X there. So alpha lies this this so alpha lies outside this ball. Okay, so because of this thing, so distance of X to alpha, so this will be greater than equals to capital R plus small r. Okay, so that thing I have mentioned it here. So from these two equations, so what we have? So we have this thing here. So we have this thing here. Okay, so let us call the start equation. So again, note this. So what is the definition of this n? So 2 to the power n minus 1 is less than length of alpha, less than equals to 2 to the power n. Okay. And now if I take log 2 all the sides, so we have this thing. Okay. And now you put this thing in this equation. So what we have, so R is less than equals to, so R is less than equals to n plus 1 delta plus 1, and n is less than this thing. So this part I have put it here. So therefore, eventually what we have, so length of alpha is greater than 2 to the power R minus 1 by delta plus 1 minus 2. Okay, so this length of alpha is greater than, so this right hand side, it is this some kind of exponential of function of this R, right? Okay, yeah. So we have observed this thing. Okay, so now let me come to the formal definition. So we have proved this thing. So alpha, it is a path lie outside this ball, that ball. So length of alpha is this thing. Okay, so we'll say that geodesics in hyperbolic metric space diverge exponentially. Okay, so now let us come to the formal definition of this divergence function. Okay. So we say this function e from this non-negative set of real numbers to R, this e is a function from this to this, is a divergence function for a metric space X. So if for all points X in this metric space and all geodesics gamma and gamma prime, so gamma prime is starting from X. So this is the notation of geodesic joining X and Y. So gamma is a geodesic joining X and Y, and gamma prime, it is a geodesic joining X and Z. So for all geodesics gamma and gamma prime from X, the function E satisfy the following thing. So for all this non-negative numbers, capital R and small r, such that So this capital R plus small r is less than the minimum of the length of these two geodesics. Okay, and if uh, distance of gamma r and gamma prime r is greater than E0 and alpha is a path lying outside this ball of radius capital R plus small r around x, joining these 2 points, gamma r plus r, gamma prime r plus r. So length of alpha is greater than e to the e of r. Okay, so if this happens, we call this e to be a divergence function. Okay, so this is a general definition of this divergence function. And if for a metric space there exists a divergence function which is exponential, so then we say geodesics in X diverge exponentially. Okay, so what we have shown that so geodesics in a hyperbolic metric space according to this definition diverge exponentially. Okay, all right. Any question?
In the definition, if I take E to be constant minus 1, then it satisfies the whole condition. So that also a divergent function, right?
Which one? E to be minus 1. That is also a divergence function. So if we take, yeah, so obviously that will be a divergence function. But so I want for in a hyperbolic metric space a divergence function which is which is exponential in terms of r, right? So that part we have shown. Obviously, there
I
can
didn't get
exist
what
some other divergence function, but
I didn't
what
get.
we want.
Oh,
Okay.
what is his question? E equal to
So I
minus.
can take just E of R to be equal to your -1 for all R belongs to this thing. Obviously, this will be a divergence function according to this definition, but this is just a constant thing, right? So length of any path. So this will be obviously greater than equals to -1. Right? Length of anything will be. So this will be a divergence function, but what we want here in this hyperbolic metric space, we want a divergence function which is exponential. Fine. Any confusion? Okay. Yeah. Any question? Okay. So in fact, the converse of this is also true. So converse of this is also true. So converse of what? So if I, okay, I'll just write it here. So what we have proved that, so this shows that, so geodesics in a hyperbolic metric space diverge exponentially. Okay, so this part we have shown, and the converse is also true. So converse is so conversely. So if in a geodesic metric space, so geodesic diverge exponentially, meaning that there exists a divergence function for geodesics which is exponential. Then so if I call it to be x, then x is a hyperbolic metric space. Okay, so the converse is also true. Okay, so the converse is also true. So the idea is basically So idea is basically the following. So if I take a triangle, so now you assume, so X is a geodesic metric space such that, so geodesics diverge exponentially. Okay, so this implies, so there exists a divergence function on X. Sorry, so there exists a divergence function which is exponential. Okay, so the idea is the following. So you take a triangle. So you take a triangle in this metric space X. All right. And now, so what you do, so first let us concentrate on this vertex X. So you take these 2 points. So let us call it to be your YT, ZT. So these are at T distance. Okay. Suppose the triangle is good enough. So I'll get some, so this yeah. So now you vary this T. Okay, so you vary this T. So this will also vary, right? So you can consider this thing. So there will okay. So there will exist some capital T here such that this will be equal to your E. Fine. So E naught, let us assume this to be this is in R. So because it is exponential, so let us assume this E of not E naught, E of 0, so is some positive number. This redundancy. Let us assume this thing. Okay. So E naught is this thing. So there exists some capital T, something like this, and for the other sides also same thing. So there exists some point such that this distance is same as this distance, and this distance is exactly equal to your E. Okay, so this distance is same as this distance, and this is exactly equal to your E. Okay, all right. Yeah. So if I pick any point here, for example, so this pick any point here, so this distance, it is at most E naught. Okay, so I'm not bothered about all these corner triangles. Okay, so these are already your slim. Okay, so these are already your slim triangles. So I'll chop out you can think in this way. So I can chop out all this corner triangles. Okay. So now what I want to show, so this length, so let us call this to be my L1, this to be this thing to be my L2, and this portion is my L3. Okay. So claim is, so this L1, L2, L3 are bounded. Okay. So this part, you can say this is the some kind of thick part of this triangle. And this red portion, the corner triangles are thin part of this triangle. So this distance, it can be very large. This distance, it can be very large. although they are equal to each other, but this can be very large. This portion, it can be very large, but the blue sides of the triangle, it will be bounded. Okay. So how do you show this thing? So what you would assume, so L1, L2, L3, so these are the lengths. So you can assume that this, let us say L1 is bigger than L3, bigger than this L2, something like this. And then what you do, so you take this point, you divide this point. So this point, so this length is your L1 by 2. Okay, and let us call this to be my A. So you take a circle, a ball of radius. So take a ball of radius A plus L1 by 2 around this Y. Okay. And yeah, so there are several cases. I'm not going to that thing. And now if I, okay, so now if I think of this path, this, so starting from this one, going from here to here, go like this, then go like this, go like this, and then again come back here. Okay. So this path is lying outside. If I call this path to be alpha, so alpha lies outside this ball. Okay, so alpha lies outside this ball. Okay, and you have assumed that the geodesic diverge exponentially. So the length of this alpha, okay, so this will be bigger than, greater than this L1 by 2. Okay, so this one. Yeah. So you have now two geodesics. So we have this two geodesics here. So this two geodesics. So this one is your gamma, and this is your gamma prime. This point is your, say, gamma r, and this point is your gamma prime r. Okay. So by the definition of this divergence of this geodesics, so length of alpha is greater than L1 by 2. And what is this length of alpha? So this is this length first, L1 by 2. Plus E naught plus L2 plus E naught. Sorry, length of alpha is E of L1 by 2, right? Not just L1 by 2. E of L1 by 2. So this right hand side, so this is exponential. I've made this mistake. So length of alpha is this E of L1 by 2. So length of alpha is exactly equal to L1 by 2 plus E naught plus this L2 plus E naught plus plus something, let us call it to be small L3. This portion, so small L3. So this is greater than E L1 by 2. Okay. And again, the left hand side, so this L3 is less than equals to capital L3. Okay, so yeah, maybe I'll just write it here to become clumsy. So in the next step, so E of L1 by 2 is less than L1 by 2 plus E naught plus L2 plus E naught plus the small L3, you can replace it by capital L. Okay, so now this right hand side, it is an exponential function of L1, and this side, it is, so L1 also it is here, it is linear. Okay, so this will imply that this L1 is bounded. So this will imply that L1 is bounded. And I have taken this L1 to be the maximum of this L2 and L3. So this will tell you that this L2 and L3 will be also. So the details have been worked out here. Yes, so details are given here. So in fact, if I prove this thing, so I can prove more. So instead of exponential divergence function, you can take non-linear divergence function. So this is the theorem. So if X is a geodesic metric space with a non-linear divergence function E, then triangles are delta slim in X, where delta depends only on E0. Okay. Yeah. So there are several cases. I have just mentioned a general case, a simple case for that. Okay. Yeah. So I'll stop here. If you have any question, you can ask.
So under root x, is that that is also non-linear function, right?
Which one?
Under root x, I mean root.
Yes, yes, obviously, yes.
But suppose I have a geodesic metric space and whose divergence function is under root x.
Yeah. So what we get here ultimately, so we get that thing. So we'll get this kind of thing. So in that note, I have, again, you can simplify this L3, L2. So L3 and L2, it is less than equals to L1. Again, you can simplify this thing. So what equation you'll get? So you'll get this thing. You'll get this equation, right? And the right hand side is this linear. Okay. And if I take something which is non-linear kind of thing, so this will give a bound on this album.
That is the point. I mean, root x also non-linear function, but you want some function for which en by n going to infinity, something.
Correct. Yes. Or maybe if you are happy, just take e to be exponential.
Okay.
Service, please stop the recording. Yeah. Any other question? Okay. So we meet again at 4 o'clock.